This video is an introduction to Hamiltonian paths and circuits. A Hamiltonian path is a path that visits every vertex exactly once. So unlike an Euler path that has to visit every single edge, Hamiltonian paths visit every vertex exactly once. So looking at the graph on the left, does the graph have a Hamiltonian path? In other words, can you begin at a vertex and visit every vertex ending at another vertex? And the answer here is yes, we can. Several ways to do this. In fact, this path is not unique, but we could start at A and go to D, to G, to E, to F, to C, and to B, visiting every vertex exactly once. Notice what we could not do is go from A to D to E, to F to C to B, back to E, and then to G, because we traversed through vertex E twice, and that would not be allowed in order to create a Hamiltonian path. Again, not necessarily unique, but we could go from A to D to G, E, F, C, and end at B. Now, looking at the graph on the right, does this one have a Hamiltonian path? As you look at this one of the things that you might notice is that we have three vertices here, all of degree 1, F, E, and D. And in order to follow the Hamiltonian path, we have to visit every vertex, but there's no way to get out, if you will, of F or E or D once you go in. There's no way to backtrack. So while we can start at any one of those vertices, what we discover is that we get stuck. Once we go out of one of those vertices and into another, there's no way to find our way back out without revisiting a vertex we have already been to. And so in this case, this graph does not have a Hamiltonian path. A Hamiltonian circuit is a circuit that begins and ends at the same vertex. Now, just like we have circuits that start and end at the same vertex, and we have Euler circuits that begin and end at the same vertex, traveling every edge exactly once, a Hamiltonian circuit is a circuit that begins and ends at the same vertex, except it passes through every one of the other vertices exactly once. Again, the beginning and ending vertex is the exception to that rule. You do have to cross through that one twice. You have to start and finish there. So, does the graph on the left have a Hamiltonian circuit? And yes, this one clearly does. You can just kind of follow along the outer edge, if you want, of this graph, and you will find it has a Hamiltonian circuit. You could visit every vertex exactly once. Again, where you start doesn't matter. I'll pick somewhere different from what I was just tracing. We could go from D to F to G to E to B to A to C and back to D. So again, the goal is to visit every vertex, okay? Does the graph on the right have a Hamiltonian circuit? So can I begin somewhere, let's say J, can I visit every single vertex along this graph and end up where I started? So if you notice the path that I just took along the outside here, I never went to vertex D or F, okay? Well, maybe you say, well, let's start at D, okay? I'll start at D. From D, I can go up to B, over to C, down to G, then I can go around I, K, J, H, E, and then I have a choice. I can go to F and back to D, but then I never visited vertex A. And so I think you'll find that up in this section, kind of looks like the little roof of a house maybe, that this is the section that's causing problems. I can't get to all of these vertices without duplicating more than one. And so this graph does not have a Hamiltonian circuit. Now, how can we tell if a graph has a Hamiltonian path or a Hamiltonian circuit? This is one of those interesting problems where there is no good way. We just have to try it out. Okay, so we can't. We have to try it out. Okay, we don't have, there is no way to show, like with an Euler path or an Euler circuit, using the number of degrees, we can determine whether or not there's an Euler path or circuit. But with Hamiltonian paths, this one is, there is no set method that says, absolutely, this one's going to work. The only way to find one is to work at it, to practice, to see what happens. And when you've tried enough times, you kind of discover that this is where the issue lies. It's this set of vertices here, or this is the problem here. You can determine it does not have a Hamiltonian path or a Hamiltonian circuit. But again, no predetermined way to make that happen.